Humans are very curious creatures. It might even be one of the reasons why you're listening to this video. Physics emerged from this curiosity with the goal of explaining the whole universe into a single formula. The closest we've come to this goal is the Standard Model. Developed in the mid-20th century, this model has been extensively tested and confirmed through numerous experiments, and has been regarded as the most successful scientific theory of all time. But what is the Standard Model? This theory describes our universe as being composed of indivisible fundamental building blocks that we call particles. On the one hand, our universe is composed of matter. These are the fermions. They are split into 3 generations, each with 2 quarks and 2 leptons. The first generation composes almost everything we see in the universe, and the other 2 generations are particles that have exactly the same properties, except they ate a little too much on Christmas Eve. It would be a very boring universe if it wasn't for the other category of particles, which are the bosons. These particles are responsible for 3 of the 4 fundamental forces in the universe. And how can we describe the interactions between these particles? This is the realm of quantum field theory. If one were to compare an electron in our body to an electron in the sun, they would be completely identical to each other, and this applies to all particles we just described. For this reason, particles seem to be the local manifestation of an underlying object that is displaced throughout the whole universe. These objects are the fields in QFT. Their quantumness means that these fields do not have a definite configuration, but are actually the superposition of all possible configurations at any given instance. In this sense, a particle is just a disturbance that propagates within a field, and the different field configurations correspond to the different ways in which particles can interact with each other. Consider 2 electrons traveling parallel to each other. In the Standard Model, charged particles can interact with a photon field. So, there is a field configuration where they repel themselves due to the exchange of a photon. There is also the field configuration where 2 photons are exchanged, or 3, or even field configurations when one of these photons splits into a pair of particle-antiparticle that recombines into a photon, resulting in the same repulsive effect. The key point is that in any given process, all existing particles appear in every way possible. Luckily for us, the more complex a scenario is, the less important it is. And the way of calculating every possible scenario and averaging according to their importance has made the Standard Model the most precise theory ever, to explain only 5% of the universe. Of the remaining 95%, we know that at least 25% of the universe is composed of dark matter. How do we know this? Because stars are gravitationally bound to the center of galaxies, they cannot rotate infinitely fast. The mass of a galaxy is what dictates how fast stars can rotate. The problem is that we can only observe 1/10 of the mass required to explain the velocity at which we see stars rotating. This, of course, poses the question: are there additional dark massive objects inside galaxies, like brown dwarfs or black holes? Or is it just gravity that does not behave like we expect it to at such large scales? Or, even more bizarre, is there a new particle that we don't know of that's causing this increase in mass? By smashing things into each other, like a good particle physics would do, we could start to search for massive particles that have mechanisms to explain the current abundance of dark matter in the universe, and that are electrically neutral, so they don't emit light. The fact that dark matter doesn't interact with photons makes its direct detection incredibly challenging. But this is where QFT comes to our rescue. If, for any given process, quantum fields interact in every way possible, then there must also be field configurations where dark matter particles pop up, which we are missing in our current calculations. Wouldn't it be great if we could take advantage of this and indirectly predict some properties of dark matter?